Hi everyone, I am Sam. Today we are going to talk about quantum theory. For centuries, people believed that the cosmos worked like a giant clock. If you could understand all the positions and velocities of each gear in the machine, then the future would be completely predictable. This picture of a clockwork universe came from Isaac Newton's groundbreaking work in the 17th century. Newton's laws were so powerful that, for a long time, everything, planetary orbits, falling apples, cannonballs, seemed to neatly obey them. Even electricity and magnetism, explored by scientists like Faraday and Maxwell, fit into a broader scheme of predictable, continuous fields of force. But toward the end of the 19th century, certain phenomena started to pop up like pesky puzzles that refused to be solved using classical physics. One of those phenomena was known as blackbody radiation. A blackbody is a perfect absorber and emitter of radiation. If you heat up a piece of metal, it glows in different colors depending on its temperature. According to classical physics, if you tried to calculate the distribution of light, or radiation emitted by a heated blackbody, you got nonsense. Predictions that went to infinity at higher frequencies. But around 1900, a German physicist named Max Planck stepped in with an audacious proposal. He said that energy wasn't simply given off in a smooth, continuous manner, but rather in tiny packets, or quanta. At first, Planck himself didn't really believe that the energy could literally be quantized. He thought it was just a mathematical trick. Yet the idea worked so well at matching the actual measurements of blackbody radiation that it slowly began to be accepted. Although Planck kicked the door open to the quantum world, it was Albert Einstein who walked through it with confident strides. In 1905, Einstein had his miracle year, publishing papers that transformed physics. One of these papers explained the photoelectric effect. When light shines on certain metals, it ejects electrons. Classical theories said that shining very low-frequency light for a long time should gradually build up enough energy to knock electrons loose. But real experiments showed that if the light was below a certain frequency, no electrons came out at all, no matter how intense the light was or how long you waited. It was as if the metal was demanding a minimum energy entrance fee that couldn't be cheated by shining more light at a lower frequency. Einstein suggested that light itself was made of tiny energy packets, now called photons, each with just enough energy tied to its frequency. This changed the very notion of light from a continuous wave to something that could also behave like a stream of particles. For a while, people struggled with this wave-particle contradiction. When you shine light through two narrow slits, you get an interference pattern on a screen, bright and dark stripes like waves overlapping. But then, with the photoelectric effect, light seemed to act as a stream of particles. How could it possibly be both? Physicists at the time were fascinated and confused. They also started to realize that this wave-particle puzzle wasn't limited to light. In 1924, Louis de Broglie, a French prince-turned-physicist, proposed that if light waves could sometimes behave like particles, perhaps matter particles, electrons for instance, could sometimes behave like waves. It was as if the universe had a dual identity hiding in its back pocket. To most physicists back then, this sounded outlandish, yet it turned out to be true. Experiments soon confirmed that electrons shot at a crystal diffraction grating formed interference patterns, just like waves of light. This convergence of ideas, quantized energy, wave-particle duality, was laying the foundation for a new theory. But quantum theory really began to take shape in the mid-1920s. Two separate but related mathematical formalisms emerged almost simultaneously. One was Werner Heisenberg's matrix mechanics, which looked extremely abstract and complicated. The other was Erwin Schrödinger's wave mechanics, which was more intuitive, at least at first glance, because it described electrons as wave-like entities. Both approaches ultimately proved to be describing the same underlying quantum reality, just with different mathematical tools. Schrödinger's equation became a central pillar of quantum mechanics. It describes how a so-called wave function evolves over time. The wave function is a strange beast. Unlike a classical wave on a string that's physically wiggling, the quantum wave function is more like an information wave, telling us where we might find a particle if we go looking. Before we make a measurement, the particle isn't pinned down to a single location. Instead, it has probabilities of being in different places, encoded in the wave function's shape. If that seems weird, well, It is weird, and scientists at the time were in heated debates over what it meant about the nature of reality. At the forefront of these debates was Niels Bohr, the Danish physicist known for his thoughtful, philosophical approach. Bohr advocated what became known as the Copenhagen interpretation, which in crude terms says that the wave function is a complete description of a system until it's measured or observed, at which point it collapses into a single outcome. Not everyone was comfortable with this. For instance, Albert Einstein famously grumbled, "God does not play dice," reflecting his discomfort with the notion that the universe is fundamentally governed by probabilities, rather than certain outcomes. Einstein, along with colleagues Boris Podolsky and Nathan Rosen, later formulated what came to be called the EPR paradox, EPR standing for Einstein, Podolsky, and Rosen. They argued that quantum mechanics must be incomplete because it allowed for what Einstein called spooky action at a distance, referring to entanglement, where two particles could be connected in such a way that measuring one seemed to instantly affect the other, no matter how far apart they were. Meanwhile, Werner Heisenberg contributed another cornerstone, the uncertainty principle. Heisenberg's principle says that the more precisely you try to measure a particle's position, the less precisely you can know its momentum, and vice versa. It's not just about the limits of your measuring instruments, it's woven into the very fabric of nature at tiny scales. This principle profoundly challenged the clockwork vision of the universe. If you can never know both position and momentum with perfect precision, you certainly can't predict the future with absolute certainty. This was another blow to the deterministic worldview that had reigned since Newton. Amid all these staggering conceptual shifts, there was one more piece of the puzzle that clarified how to interpret the wave function. Max Born proposed that the wave function should be understood as describing probability amplitudes. In simple terms, the wave function doesn't tell you where a particle is, but rather the odds of finding it here or there. Born's rule lets you calculate the probability of an outcome from the wave function. This was an incredibly radical shift. Physics, once a science describing how objects move with certainty, had morphed into a tool for predicting probabilities. Of course, not everyone was content with probability as a final answer. Einstein spent years trying to show that quantum mechanics was missing some hidden layer of reality. However, experiments by John Bell in the 1960s, and later refined by many others, demonstrated that if nature had such local hidden variables, it wouldn't produce the statistical patterns we observe in quantum experiments. Entanglement, that spooky action at a distance, turned out to be real. This is the phenomenon where two particles can be so intertwined that measuring one changes the state of the other instantaneously, even across vast distances. While this doesn't allow for faster-than-light communication, you can't control the outcome of the measurement, it does highlight that quantum reality is bound by rules that defy our usual intuitions about space and time. Throughout these developments, physicists did what they always do. They tested the theories in labs. The most famous demonstration of quantum weirdness is probably the double-slit experiment. You take a light source, or even a source of electrons, and shine it on a barrier with two narrow slits, observing the pattern it creates on a screen behind the barrier. If light or electrons behaved strictly like little particles, you'd expect two bright bands behind the slits. If they behaved strictly like waves, you'd expect a pattern of multiple bright and dark stripes, an interference pattern. What you get in the lab is an interference pattern indicating wave-like behavior. But the real kicker comes when you try sending electrons through one at a time. Even then, each individual electron registers as a point-like hit on the screen. But as you build up more and more hits, an interference pattern emerges. It's as though each electron interferes with itself, going through both slits in some quantum sense, until you measure which slit it goes through. Once you measure, you force it to choose, and the pattern changes. This baffling result is often described as the central mystery of quantum mechanics. To highlight just how peculiar quantum mechanics can be, we have Erwin Schrödinger's famous thought experiment involving a cat. Imagine a cat in a box with a flask of poison that is released based on the decay of a radioactive atom. According to quantum theory, until we measure or observe whether the atom has decayed, it remains in a superposition of decayed and not decayed states. Schrödinger asked, "Does that mean the cat is in a superposition of alive and dead at the same time?" The thought experiment was meant as a critique of the simplistic interpretation that the wave function collapse is the only solution to quantum measurement. It sparked countless debates and has become a popular culture reference for the bizarre implications of quantum theory. But despite the philosophical and conceptual turbulence, quantum mechanics works. It works so well that it forms the backbone of many modern technologies. The design of transistors, which power all our electronics, depends on understanding the quantum behavior of electrons in solids. Lasers wouldn't work without the quantum theory of light and matter. MRI machines in hospitals rely on the quantum spin of atomic nuclei. Even your phone's GPS system relies on extremely precise clocks that leverage quantum effects. So, in a sense, our entire modern world is built upon this strange set of rules. We might not completely understand what it all means philosophically, but we certainly know how to use it. Let's return to the historical thread. After the main framework of quantum mechanics was established in the late 1920s, the next couple of decades saw enormous growth in atomic physics, nuclear physics, and eventually particle physics. Paul Dirac took quantum theory further, merging it with Einstein's special relativity to describe particles traveling near the speed of light. Out of Dirac's equations came the prediction of antimatter, positrons specifically, which were later discovered experimentally. This was a stunning triumph. A purely theoretical exploration had predicted an entirely new form of matter. During the 1930s and 1940s, quantum mechanics also became the foundation for understanding how atoms bond in molecules. Chemistry, long a somewhat separate discipline, merged with quantum physics, and the field of quantum chemistry was born. Researchers realized that the quantum mechanical behavior of electrons was responsible for the periodic table's structure. With each element, the electrons fill up orbitals, defined by quantum rules that depend on the atomic number, leading to recognizable chemical properties. This new perspective explained why, for instance, sodium and chlorine, on opposite sides of the periodic table in certain rows, bond so well together to form common salt, whereas other combinations are less stable or don't bond in the same way. The nuclear age, unfortunately, arrived with terrifying consequences during World War II and its aftermath. Nuclear fission, explained through quantum tunneling and other nuclear processes, led to the development of atomic bombs. The subsequent arms race spurred major developments in particle accelerators and research into fundamental particles. Physicists discovered that protons and neutrons were themselves made up of quarks, bound together by gluons, all described by a quantum field theory called quantum chromodynamics, QCD. Meanwhile, another quantum field theory called quantum electrodynamics, QED, became one of the most precisely tested theories ever, accurately predicting results to many decimal places. All this underscores that quantum mechanics was not just a quirky corner of science. It had become the language through which physicists describe the building blocks of reality. Philosophically, the debates never truly ended. Einstein's challenges to quantum mechanics were taken up by others. Even to this day, interpretations of quantum mechanics abound. There's the many worlds interpretation, which posits that every quantum event spawns multiple branches of the universe. There's Bohmian mechanics, which tries to restore a sense of determinism with pilot waves. There are also relational and informational interpretations that suggest reality is fundamentally about the relationships between observers and systems. While these interpretations differ on the question of how to picture quantum reality, they all share the same underlying mathematics that has been confirmed by experiment again and again. So how might we wrap our heads around it all, especially if we don't have a deep academic background? One way is to try to see quantum theory as a story of shifting perspectives. We used to think reality was entirely knowable through deterministic laws. We believed objects had definite properties at all times: position, velocity, color, everything set in stone, whether or not we were looking. Quantum theory tells us, in essence, that nature on the smallest scales might not be pinned down until it interacts with something else, like a measuring device or an observer. This interaction forces the quantum system to make a choice, which reveals itself as a definite outcome in our macroscopic world. Between interactions, particles, or waves, or both, are governed by a wave function that evolves in a mathematically precise but conceptually baffling way. Is that wave function real? Or is it just our knowledge about the system? Quantum mechanics shrugs and says, Either interpretation works, as long as you can calculate the probabilities correctly. This can be deeply unsatisfying if we want a clear picture of what is objectively going on. But it is a testament to the power of mathematics and experiment working hand in hand. We might not fully grasp what it is, yet we can measure phenomena, predict outcomes, and build technological marvels from these predictions. Another key takeaway is how intimately tied together everything becomes at the quantum level. Entangled particles challenge the notion that objects have separate, independent existences. In quantum theory, measuring the spin of one particle can set the spin of another, even if it's light years away, without any classical signal traveling between them. Again, this doesn't violate the speed of light limit for communication, but it shatters the classical concept of separability. As you step away from this story, you might be left with more questions than answers. That's totally normal. Quantum theory is designed, in some sense, to make us feel a bit uneasy. We might be tempted to say, okay, so everything is random? But that's not entirely the point. Randomness in quantum mechanics is not the same as chaos or meaninglessness. Rather, it's a tightly constrained randomness, governed by strict mathematical rules. When you roll a pair of dice, the probabilities of landing on any given number are uniform. But in quantum mechanics, the probabilities are shaped by wave functions that evolve according to Schrödinger's equation. So it's not total randomness, but rather a new kind of lawfulness that deals in probabilities instead of certainties. If you're still pondering how a particle can be in multiple places at once, or how it can behave like both a wave and a particle, you're in good company. Generations of physicists have grappled with the same puzzles. Richard Feynman, one of the most brilliant physicists of the 20th century, famously quipped, "If you think you understand quantum mechanics, you don't understand quantum mechanics." Yet Feynman himself developed a powerful reformulation of quantum physics known as the path integral, which pictures every possible path a particle might take as contributing to its overall behavior. The final outcome, after considering all possible paths, is what you actually observe. Again, it sounds bizarre, but it provides extraordinarily accurate predictions. In the present day, quantum theory is at the heart of some of the most cutting-edge research. Quantum computing aims to exploit phenomena like superposition and entanglement to process information in ways that classical computers can't match. Quantum cryptography uses the laws of quantum mechanics to create secure communication channels that, in principle, can't be hacked without alerting the sender and receiver. There's also quantum metrology, which uses quantum effects to build sensors of unprecedented precision, useful for everything from gravitational wave detection to better medical imaging. All these applications highlight the fact that quantum mechanics isn't just an abstract intellectual exercise. It's an astonishingly robust framework that keeps proving itself useful. That said, it also forces us to revisit the question of how we define reality. Is reality what we can measure and predict, or is it something deeper that might always remain hidden from direct observation? For some physicists, the question isn't worth the headache as long as the equations work. For others, it's the core puzzle that drives them forward, seeking a more complete understanding. There's also the quest to unify quantum mechanics with Einstein's general theory of relativity. We know quantum theory excels at describing the small, and relativity excels at describing the large. Stars, galaxies, black holes, the curvature of space-time itself. But these two theories haven't yet been stitched into a single coherent framework, especially in extreme conditions like the center of a black hole or the beginning of the universe. So there's still a grand challenge awaiting future physicists. A quantum theory of gravity that might finally reconcile the weirdness of the small with the grandeur of the large. So as you walk away from this whirlwind journey, keep in mind that quantum theory started from a handful of nagging puzzles that classical physics simply couldn't solve. Bit by bit, a new understanding emerged, shaped by icons like Planck, Einstein, Bohr, Heisenberg, Schrödinger, Born, and many others. They proposed radical ideas: energy quanta, wave-particle duality, uncertainty, entanglement, probability amplitudes. These ideas weren't just theoretical indulgences. Each one was tested in experiments, and each one passed the test. In the process, our picture of reality was forced to expand. It's easy to think of these great figures as detached geniuses, but in reality, they argued fiercely. They took leaps of faith. They made mistakes and corrected them. Quantum mechanics was a communal effort, a gradual awakening to the fact that nature at its core doesn't behave like a big machine with tiny gears. Instead, it behaves like a cosmic dance of probabilities, waves of possibility, and interactions that defy our everyday expectations. If it all seems too strange, remember that centuries ago, the Earth orbiting the Sun also seemed absurd to many people. Understanding often follows acceptance. And in the quantum realm, acceptance means letting go of some of our most cherished classical assumptions. This letting go can be disorienting, but it also opens the door to fascination, creativity, and technological breakthroughs. After all, we don't need to fully grasp the inner workings of quantum reality to use it to our advantage. But the very act of trying to comprehend it can broaden our sense of wonder and remind us that the universe holds surprises that we are only beginning to uncover. In the end, quantum theory is more than just a set of equations or quirky lab results. It's a testament to human curiosity and our willingness to challenge assumptions. It shows that even the seemingly solid aspects of our world, like electrons orbiting in atoms or photons shining from a lamp, are governed by principles that can make our heads spin. Yet, out of that head-spinning confusion comes a deep sense of awe. Quantum theory, for all its strangeness, is a triumph of reason and imagination working together. It has reshaped our understanding of what's possible and continues to guide us toward the next horizon of scientific discovery. And in a way, that's the most exciting part. While we stand on a century of quantum knowledge, the journey is far from over. We can only guess what new revelations and technologies await us as we push the quantum frontier further. Until then, we can appreciate the remarkable fact that the everyday objects around us, computers, phones, lights, are powered by principles that, not too long ago, were considered utterly bizarre. And that might just be the perfect reminder that the universe is full of wonders that can change our world once we dare to explore them. That's it for today, and I'll see you in the next episode.